All right, so this is the setup of the question. That means that this person is 800 newtons and this person is 600 newtons. And in the first part of the problem, I believe they ask, what is the normal force on the 800 Newton person as they stand on the floor? So can we all agree that this problem is a problem in which the net force equals 0? Because nobody's moving, right? So net force equals 0 here, and net force equals 0 here. I believe there are two forces acting on the 600 Newton person. There's tension upwards and weight downwards. And I believe there are three forces acting on the 800 Newton person. There's weight downwards. There's tension upwards. And there's normal force upwards. Any questions yet? All right. Tension plus normal equals 800. Is that okay? And tension equals 600. So normal must equal 200. I know that's not the question you had. You have a question on part B. We might as well start here, right? Now, the person who is hanging is going to begin to climb the rope. And they're going to accelerate upwards. Can we all agree that the only way they can accelerate upwards is if the tension on them increases to be greater than the weight? Can we all agree with that? Any question about that? Okay. So that means the net force on them is no longer going to be 0. Thank you. But will be MA. Go ahead. Mm-hmm. So them climbing up the rope, that increased the tension and that caused it to shift. Right? Well, I don't know if it caused the rope to shift any, but they're climbing up the rope. Right. The question said that it lifted the 800 person. But right now we're just focusing on what's happening to the 600 Newton person. So we'll have to handle what happens to the 800 Newton person now. Okay? But would you agree, though, that the only two forces acting on the person are still tension and their weight? And by them pulling down, you guys have seen somebody climb a rope or climb one yourself? You pull down on the rope, so the rope will pull up on you. They have pulled down on the rope, increasing the tension on them, so they will accelerate upwards. That means the tension is no longer 600 newtons. The tension must be something greater than that. The person who's standing on the floor, it says, how fast do you have to accelerate to just begin to lift the other person off the ground? Just begin to lift the other person off the ground. It sounds to me like the normal force is going to be reduced to 0. That's the instant they get lifted off the ground. It didn't say that they were accelerating. It just says they just begin to get lifted off the ground. It's going to take, 800 newtons of tension to begin to lift an 800 Newton person off the ground. So tension in the rope must increase to 800 newtons. If the tension in the rope increases to 800 newtons on a 600 Newton person, then our 60 kilogram person is going to accelerate off the ground. They are 60 kilograms because they are a 600 Newton person. Their mass must be 60 kilograms. So 200 over 60 has to equal the acceleration of the person necessary to lift the other person off of the ground. 10 thirds? So 3.3 meters per second squared would have to be the person's acceleration in order to just begin to lift the other person off the ground. I think it's an unusual problem, but I think it's kind of neat too. So that's why I included it. I think if I gave it to you on your test, you guys would probably be unhappy. But I think as a homework question, this is a solid homework question. I think it asks reasonable things. But would you like to follow up with some follow-up questions for me on it? All right. Then let me throw at you guys a little bit of wisdom. Threshold problems like this are almost always going to be about normal or tension going to zero. Since tension can only pull and can't push, when you establish the direction for a tension, the smallest the tension can ever then become is a value of zero. Similarly with normal force, once you have established its direction in your problem, the smallest it can be is zero. They can't switch directions. So normal doesn't switch direction and tension doesn't switch direction. The floor can only push up. The floor can't pull down. So if we're looking for a problem that deals with threshold, then look at your normal force. It's the thing that responds. Or look at your tension force. It is the thing that responds. It can change. Their weight can't change. Weight has to stay the same. Okay, that's nice. I don't mind stopping everything. M1 and M2 are hung on either side of a frictionless and massless pulley. Find an expression for the acceleration of the system and describe how you could determine the acceleration of gravity using this system. All right, so this is the lab we are going to do. I told you we're going to determine the acceleration of gravity a couple different times. We did the first part of this problem, I believe, in class yesterday. So I'll reiterate it only because I think if asked for you guys to do it, I'm not sure what your level of success would be. It'd probably be pretty good, actually. But let's take a few minutes and at least kind of redo it. So I've got two objects on a standard Atwood machine. Yep. So yeah, it would be quite different. So something that looks like that. And M1, M2. Now, we're assuming a frictionless massless pulley, but we do have to determine what we feel is going to be the positive direction for this problem. Looking at the pulley, do you want to go clockwise or counterclockwise? Okay, that's fine by me. This decision about what you're going to make positive is an arbitrary decision. You make the decision so that you are consistent in your application of positive and negative. And I've been working with, I had some students in here for tutoring this morning, but more importantly, when I say the word arbitrary, I think students think it's unimportant, and that's actually not the definition of arbitrary. It's exceptionally important that you make a decision about what direction you're going to call things for positive and negative so that you have consistency across your problem. If you don't do it this way, you've got to find a different method for consistency. I like this method because it works for my sensibilities. The book provides a different method. I could go over the book's method if you wish. The problem with the book's method is it's quite different than this, and I don't want to confuse anybody. But you have to find a way to indicate direction that allows for consistency on both sides of the pulley. If you don't make that statement, everything is wrong from this point forward. So some things are obvious and relatively easy, and you never make the mistakes. So there's nobody in the room who's going to not know, all right, it's a dot, and I have probably an arrow down and arrow up. I mean, people do that kind of stuff because they've been doing it the whole year and figure that they can't get that wrong. I mean, I do worry about the people who have this problem and have arrows to the side. It means that they're not really paying attention, or they don't really know what's happening. For us, direction ends up being positive and negative, and that affects all of our equations from the point we start the problem till the end. So we're deciding to make downwards positive on this side of the problem and upwards positive on this side of the problem. And when our pulleys have mass next semester, we'll be saying that counterclockwise is going to be the positive rotational direction. So there's more than just setting an arrow. We are trying to develop a certain amount of consistency across the course of the problem. The way the book does it is to create a coordinate system, and everything in your coordinate system is always the same, no matter what. So you would always draw your coordinate system on every object the same. However, if you know your object is going down, then when you do MA, you intentionally put an acceleration that's negative. So the book does it. I find that more students make mistakes here, which is why I choose not to teach this method. But the book's method has a lot of validity. You could try it. It helps with dealing with torque, which is something we'll be talking about next semester, and the way in which forces cause things to spin. So when I say check out what the book has to offer, I know that I'm speaking definitely to a lot of students who will never possibly crack open the book or open the digital text. But if you're having difficulty with these, if you're never getting them right, and you would like to pass your next test, the book's the way to go. My voice is not the only authority on this and shouldn't be. And also I got into an argument with somebody yesterday about this, and I want to kind of clarify something here. Eventually, you have to be in charge of your own learning. I believe that time needs to happen in high school when you can still make mistakes and have somebody here to watch over you. If that time becomes college will be a miserable experience for you once the money runs out, and it will run out. It won't be miserable until that point. Until that point, it'll probably be just fabulous. But eventually the money runs out for everybody. Unless you have super wealthy benefactors or a sugar daddy or sugar mama, those things can help too. So perhaps I haven't really looked at the possibilities of the way college works. It didn't work out that way for me, but who knows? You guys might be exceptional. All right. I'm glad I recorded that. Send that on up to YouTube. So, can we kind of agree that tensions have to be the same size upwards? And in order to demonstrate that our system is going to rotate this way, I'm making the decision that M2G is smaller than tension and M1G is larger than tension. The pictures are important, and I'm going to be probably pretty critical on your test. This side, I'm going to say net force equals M2A. This side, I'm going to say net force equals M1A. By choosing a consistent direction for positive, A is the same for both of these objects. And so all I need to do now is apply direction appropriately to my vectors. So T minus M2G equals M2A. And M1G minus T equals M1A. Everything good so far? Got to add these two things together. And we did this right at the end of class yesterday, I believe. So I'm going to reiterate that substitution here is messier than just stacking the equations together. I would get into the habit of finding a way to simplify your algebra. Oops. You guys generally aren't super successful algebra students. So finding a way to make your algebra easier has kind of been a goal of mine. You stack the equations, you're going to figure out whether you've gotten this right or not pretty straightforward. Like you should get the sum of the masses on one side with the acceleration, and your internal forces should cancel out. That's how you know you've kind of done it right. The left side of this is the external forces acting on the system. Gravity is pulling down on these two masses. That's causing the system to rotate. Thus, I see the difference between those two forces. Also, we chose an arbitrary direction for positive. What if M2 was just denser than M1? Well, this would turn out to be negative. And that would tell us that it accelerates the other direction. Anytime you have a negative sign in a formula, you should stop and look at what it means to be positive or negative. Folks, if you want to know how to get more points on your tests, because the tests are only getting harder from here. Remember, I'm going to ask you to interpret an equation. What will it mean? What would have to happen for this to take place? Look for a negative sign. A negative sign in an equation gives you the possibility of a positive answer, a negative answer, and a zero for an answer. Those all have important implications. If the negative's in the denominator, you have the possibility for a system that has an impossible answer, because I can create a zero in the denominator. That's an impossible answer. You need to be very aware that that's where I live when it comes to trying to come up with a question for you guys about what would happen if these parameters changed. I look for negative signs because they have critical points associated with them. We didn't find the tension. We should work that problem out because that has complicated algebra. But to answer this question, how would you determine the acceleration of gravity? That's actually that's a valid problem. One that I would probably want to do as a lab. So if you'll remember, you have to linearize your data and you want to determine G. One way to do so is by solving this for G and turning that into your lab. So it seems to me that if you set up one of these things and measured the two masses and then measured the acceleration of the system, you could probably figure out G. So we're going to do that as a lab next week. It's not particularly hard, but you have to measure the acceleration of one of the two masses, and they're both moving at once. So we got to find a way to deal with our equipment. It's not hard. You just got to put a piece of cardboard between them, but you'll have to figure that out. So that's going to be our lab next week. So that's the answer to question 4. Question 4. On the other hand, I'd like to solve for the tension here because I would expect you to be able to do this. And it's not straightforward. You have to solve this for A to do so. And when you solve this for A, you get M1 minus M2G over M1 plus M2. Now, to find what the tension is, you have to take all of this and plug it in for tension. That may sound like small potatoes, but it's a mess. So let's do this. Let's have this mess and kind of figure out what to do. So I'll move that all over here. And this is shifting from your homework to your notes. I would have this in your notes. M1G minus tension is going to equal M1 times A, which is all of this stuff. M1 minus M2G over M1 plus M2. So there we have we've substituted in for acceleration, and now we can get an expression for the tension. But this is unpleasant to behold. So we want to solve for tension, which means I'm going to add tension to both sides. And then I'm going to take this term and subtract it from both sides. So you guys have to, do all sorts of rewriting. I'm just going to do that. Now, you wouldn't be allowed to leave it like this, but this is kind of a mess. Wouldn't you agree? I'm going to do the algebra on this, but note that I probably wouldn't ask you guys to do the algebra on this because you have to get common denominators. So to get common denominators, I have to multiply the top and bottom of this by m1 plus m2. And I know this looks like hell, right? Just terrible. But stick with me, if you will. You notice that the bottom has a common denominator, right? So I'm going to, this is a lot for 8 in the morning. I'm going to distribute so that I'll get m1 squared times g, that's this distribution, plus m1 m2 g, that's this distribution. Then m1 times g with a negative sign in front of it. So m1 squared g, that's the first distribution. And then this and this, negative, negative makes positive. So that's going to be m1 m2 g equals t. Wow. It's a lot, but I've done all the distribution now, so I can collect like terms. Yes, sir. Where? This one's m1 squared. No, it's m1 times m2, so it'd be m1 times m2. Is that okay? We're all following? Maybe a little bit? Clinging by a thread? Yeah. Can I explain the middle step? I don't even know what the hell you're talking about. Like how I got this term? Yeah, okay. I took this and multiplied top and bottom by m1 plus m2. That okay? Now, folks, I know this is a lot. I would not expect you guys to think to do this, which is why I'm the teacher and I'm supposed to come up with this stuff to show you. And the reason why I need to do this is you need to see something. So this term and this term go away. I knew that was going to happen because I've done this before. These two terms are the same and can be added together. So I get 2 m1 m2 over m1 plus m2 all times g equals the tension. Now, that's a lot of algebra, but what we get is pretty simplified. And I know you won't see it like this, so let me help you see it this way. The top is kilograms squared. You see that? Right? M times m is kilograms squared. The bottom is kilograms plus kilograms, so the bottom is just kilograms. So this whole fraction is kilograms squared divided by kilograms. So this whole fraction is kilograms times g gives us a value that's in newtons. That's how you check to see if your algebra is done correctly. You check the units. I've successfully checked the units. I'm pretty sure my algebra is done correctly. Now, here's the things that you should think about. We know that if the two masses are the same, the system doesn't accelerate, right? If I hang the same mass on both sides, will the system accelerate at all? No, it should just sit there. If we look at our acceleration right here, If m1 equals m2, the acceleration is 0. That's what we expect. If we look at the tension, m1 equals m2. Well, then I get 2 m1 squared divided by m1 plus m1 times g, which, do you notice, that's going to be 2 m1 squared divided by 2 m1. 2's cancel, one of the m1's cancel, and the square goes away, and I'm left with just the tension is mg. If m1 and m2 are the same, the tension is just the weight of one block. Remember how we had the table with the weights hanging off both sides, and I asked about what the tension in the string should be? We said if it wasn't moving or accelerating, the tension should be the weight of one block. The weight of one block. These formulas look just overly complicated, and they might be. But I don't know if you guys know this, but this is a formula you've done in algebra. It doesn't look like it, but it is. You've done a weighted average in algebra before. It's been a lot of years since you did a weighted average, but you've done one. This is a weighted average. It gives more priority to the heavier mass, which means the tension in a rope is more prioritized by which of the two masses is bigger. And that should make sense, that it would be the more important mass. All right, I wanted you to see it. The algebra is a lot. Would you be expected to do that level of algebra on an exam? I would hope not. That would be hard even for the mechanics students to do. So I wouldn't really expect that to be the level of, because most students can't do this kind of combining of the denominators. That's why I'm here to help you. All right. Anything else in the homework you'd like me to discuss? Yes, ma'am.
Can you do number 3 of the train style problems?
Yes. There are 15 toy rail cars. So I'm never going to deal with all 15 cars. Let's take a look at the entire train. The mass of the entire train is 3 kilograms because it's 15 times 0.2 kilograms equals the mass of the entire thing. And it's being pulled to the side with 3 newtons of force. There's no friction. Net force equals ma. 3 equals 3a. So the acceleration is 1 meter per second squared. Everything okay so far? I'd like the tension between the 7th and 8th car. Okay. Again, I'm not gonna deal with the whole train. Let's deal with 2 train cars. I think there is there's 7 train cars here, and then a coupling, and then 8 train cars here, and a coupling right here in the middle. So this one is 8 times 0.2, or 1.6 kilograms. And this one is 7 times 0.2, or 1.4 kilograms. And it's still being pulled with 3 newtons of force. But at this moment, I know that the acceleration of the system is 1 meter per second squared. So this train car is experiencing just one tension. This is the tension between the 7th car and the 8th car. And that tension is accelerating those 8 train cars. The net force has to be 1.6 newtons, and there's only one tension to the right that causes that. This has to be the tension between cars 7 and 8. I don't have to do all 15 cars. The last car, well, the last car is just one little box all by itself. So I've got, 14 rail cars. And then one wee little car all on his own. Ground. Junction. So he's over there all by himself, experiencing tension in this way. Net force on him has to be equal to MA. So I think the tension must be 0.2 newtons. How's that? You can do it the hard way, but I want to connect the dots that we don't have to. We can do it the easier way. This would also work if the cars were all different masses. You just have to know all the different masses and where they were and redistribute them. This would also work if there was friction, as long as the friction was the same coefficient on all of the things. There are 2 times doing this won't work. So let me tell you what those 2 times are, since you want to study tonight. The first time is going to be if the coefficients of friction on different objects are different. If each object has a different coefficient of friction, you can't do this. You have to study them individually. And this also will work if all of this is on a ramp, by the way. If you have 3 boxes in a row on a ramp, you can still do this kind of stuff, as long as the ramp is the same angle for everybody. If your ramp has boxes at different angles, this doesn't work. You have to study them individually. So a problem like this